Good morning friends, myself Ankush Gupta here at the Gate Coach, and today in this video we are going to discuss the solutions for Gate 24 Chemical Engineering exam paper, and in this part of the video we will talk about the heat transfer subject. Okay, so there were 4 questions from the heat transfer subject for 6 marks, 2 questions for 1 mark and 2 questions for 2 marks. So let's start. First question was question number 27 as per this paper. This was the question for 1 mark MSQ. For Prandtl number equal to 0.01, which one of the following statement is true? So all of us already know that Prandtl number in heat transfer can be defined as the ratio of momentum diffusivity to the thermal diffusivity. Or based on boundary layer theory, we can also define this as the ratio of hydrodynamic boundary layer thickness to the thermal boundary layer thickness. Okay, so here as given, Prandtl number is 0.01, which means less than 1. So it is obvious that kinematic viscosity, or you can say momentum diffusivity, will be less than the thermal diffusivity. So option D will be correct. Plus, you can also see that hydrodynamic boundary layer thickness will be less than the thermal boundary layer thickness. So that is option B. So option B and D will be the 2 correct answer for this. So all of you who have taken B and D will get full marks. Next question. From this paper it was 34. One easy question. From conduction, the opposite faces of a metal slab of thickness 5 cm. Suppose this is a metal slab of thickness 5 cm and thermal conductivity 400 watt per meter per degree Celsius are maintained at, let's say T1 is equal to 500 degrees Celsius and other side T2 as 200 degrees Celsius given. Assume the heat transfer is steady state and occurs only in one direction perpendicular to the faces, means in this direction we can say, and area of each face is also given as 0.02 meters square. So they are asking what will be the magnitude of heat transfer rate in kilowatt. So from Fourier's law of heat conduction, we know that Q can be written as minus Ka dt by dx if we consider this direction to be our x direction. And here you guys can see the thermal conductivity of the slab is given 400, which is constant. So you know that if thermal conductivity of a solid is constant, so the temperature gradient will also be constant, okay, at a steady state. So dt by dx will be constant, which we can also write it as del t over del x in that way, since it is constant. So based on 2 sides we can write like this. So when you put these values, the equation will come out turn to be something like this. Here you can put the values. K is 400 watt per meter per degree Celsius. Area is 0.02 meter square. Delta T means T2 minus T1. 200 minus 500 degrees Celsius over delta X, which is 5 centimeter, or you can write it as 0.05 meter in SI system. So when you solve this, you will get your value of Q, that will be around 48,000 watt. Since they are asking in kilowatt, so you can write 48. 1 mark question again, easy one. Okay, now let's move to the next 2 questions of 2 marks each. One is 37 and other one is 38. Yes, So first, let's talk about the question number 37. The temperature of two large parallel plates of equal emissivity are 900 Kelvin and 300 Kelvin. So suppose these are the two parallel plates. First plate is at 900 Kelvin, second plate is at 300 Kelvin. Having same emissivity, let's say epsilon. Okay. A reflection radiation shield of low emissivity has been placed in between them with no conductive resistance. So let's say this is the thermal radiation shield which we have placed having temperature T3 Kelvin, suppose, with low emissivity, let's say epsilon s, the emissivity of the shield. So at a steady state temperature, at a steady state process, what is the temperature of the shield? They are asking. So I hope you know that when we talk about the two plates in general, suppose if we have two plates, the net heat transfer between the plates, Q net, or you can say Q12, we can write as sigma T1 power 4 minus T2 power 4 divided by the surface resistances, that is 1 upon A epsilon 1 plus 1 upon A epsilon 2 plus space resistance, that is 1 upon A F12, provided that the area of two parallel plates is same, that is A. So based on this equation, we can solve this. So at a steady state as given, we know that the rate of heat transfer across the arrangement will be constant, since area is also constant. So we can say that the heat transfer rate between the first plate and the shield and heat transfer rate between the shield and the second plate will be same. So you can put the values for first assembly, that is first part, first plate and shield. You can write it as sigma A T1 power 4 minus T3 power 4, that is the temperature of the shield, divided by 1 upon epsilon for the plate plus 1 upon epsilon s for the shield plus 1 upon F13, and similarly for shield and second plate it will be like sigma A T3 power 4 minus T2 power 4 divided by 1 upon epsilon s shield, 1 upon epsilon for the plate plus 1 upon F32. Since these are two parallel plates, so you know that view factor will be 1, that is F13, F32, both will be same, equal and 1. Okay, epsilon is same, epsilon s is same, so the denominator part will get cancelled, and ultimately we will left with T1 power 4 minus T3 power 4 equal to T3 power 4 minus T2 power 4. So you can write T3 is equal to T1 power 4 plus T2 power 4 divided by 2 whole power 1 by 4. So here you can put the value of T1 and T2, that is 900 and 300 Kelvin, and after solving you will get A. The correct answer will, when you will get exact answer will be somewhere around 759.14 Kelvin, which as per the option you can choose as option A. 2 marks question, easy one. Okay, we have done so many questions in the classes on radiation shield, so I hope, and since it is also one of the important topic, so I believe that all of you have done it already. Okay, so next question, that is from the double pipe heat exchanger. Hot oil at 110 degrees Celsius heats water from 30 to 70 degrees Celsius in a counter current double pipe heat exchanger. So that means if you try to draw a double pipe heat exchanger, suppose something like this. So hot oil enters. Since it is a simple assembly, so we don't need to think much. We can directly say that hot oil is entering here at temperature Thi is equal to 110 degrees Celsius and leaving on this side hot oil out at temperature Th0. And the cold water is entering in opposite direction in this annulus region at temperature, let's say Tci equal to 30 degrees Celsius and leaving here at temperature Tc0 equal to 70 degrees Celsius as given. So here you can simply, we need to find out the heat transfer rate area of heat transfer. So you know the equation UA delta T ln. Okay, U is given, delta T ln we need to calculate, Q we need to calculate, and we will get A. So QU, basically the heat duty, will be same as the amount of heat exchange between the fluids. So you know the energy balance, heat lost by oil or hot fluid will be same as heat gained by cold fluid, or you can say water. So heat loss will be mass flow rate of hot fluid, Cp of hot fluid, temperature difference of hot fluid, inlet minus outlet. Heat gained by cold fluid will be mass flow rate of cold fluid, Cp of cold fluid, temperature difference of the cold fluid, outlet minus inlet, and that will be same as your heat duty, Q. So here you guys can put the values, they are given. Mass flow rate of hot water is given, hot fluid is given 50 kg per hour or minute. Cp of hot fluid is given 2 kilojoule per kg per degree Celsius. Thi 110 degree Celsius, Th naught is unknown. For cold fluid it is 100 kg per minute. Cp is 4.2 kilojoule per kg per degree Celsius, and temperature difference is 70 minus 30 degree Celsius. The units are consistent on both sides. So when you guys will solve this, you will get two values, one for Q, which will be around 8400 kilojoule per minute, and you will also get Th naught, which will be around 68 degrees Celsius. Okay, so now we got the all four terminal temperatures. So we can draw the temperature distribution profile. Thi, it will decrease along the length of the heat exchanger, and Tci, that will increase along the length of the temperature for counter current assembly. So here you can see the temperature difference on this side of the terminal, delta T1 will be Thi minus Tc naught, that is 110 minus 70 equal to 40 degrees Celsius, and delta T on this side of the terminal, delta T2 will be outlet temperature of hot fluid minus inlet temperature of cold fluid, that is 68 minus 30 equal to 38 degrees Celsius. So you guys can easily calculate the LMTD now. I believe you know the equation. So here when you put the values, you will get delta T ln approximately 38.99, or we can write it as 39 degrees Celsius. So we got the final LMTD, we have Q. Now put those values here and you will get A. But the thing you have to do the unit conversion, because here A will be equal to Q upon U delta T ln, and when you put the values, Q will be 8400 kilojoule per minute, U is 200 watt per meter square per degree Celsius, delta T ln is 39 degrees Celsius. So U is in watt and meter square, and Q is in kilojoule and minute. So you need to change that into watt, or you can change this watt into kilojoule per minute. So let's change this kilojoule and minute into watt. So we know that 1 kilojoule is equal to 10 to the power 3 joule, and 1 minute is equivalent to 60 seconds. So now this will be converted into joule per second, and you know that joule per second means watt. So when you solve this, you will get A is equal to 17.95 meters square, means option A. Okay, so this is something about the heat transfer, guys, which was very easy, all the 4 questions in this year paper, direct equation based. So now that's all for the day. Thank you, see you, take care, bye bye.